sorry, as usual, I had to change the battery. So I was talking about the modulation, PWM modulation, sinusoidal PWM for a unipolar. So we would have the same, exactly the same carrier signal, but our modulating signal for this one would be also a sinusoid. It would have the same magnitude and frequency as the other modulating signal, but it would have 180 degrees phase shift. Basically, you're just inverting this. So it would look like this, right? So whenever this is in peak, this is going to be in the minimum and the other way around. Okay, so 180 degrees phase shift between these two. Okay, and once this happens, then what we end up with, we're gonna end up with a train of signals instead of just having, let me actually do like, this is what we had for unipolar. So like, this is what I told you like about like having just one pulse. And right, we had like a, let's say like if you start from 0, it goes like this, goes down, it goes down more, and it goes up, and it continues, right? So this was only one pulse. Now let's see how it looks like with PWM modulation, especially if you do sinusoidal PWM modulation. This was our voltage, this is our current. With sinusoidal PWM, it would have something like this. It would have a train of signals. So whenever this, these two basically cross each other, like one becomes bigger or smaller than the other one, we would have a gating signal. So like this is what we end up having, something like this, right? This basically mimics a sinusoid. You'll see how a little bit later. Okay, I don't think I have a space for the other one, but let me just like do maybe one. And it would continue. It would have basically the same thing opposite in this way. So this is how our voltage is going to look like now. We have multiple pulses. The frequency of these pulses depends on the frequency of the carrier. The frequency of the overall signal depends on the frequency of the modulating signal, right? So this would repeat itself. This will repeat itself. If I want to show you here, this is basically what we end up with. If you had PWM modulation, it would look like, this would be a little bit maybe bigger. Like I'll just like do it as, so this is what we end up with if you did PWM, but of course with more pulses. And here we would have something like that. Okay, so if I do it, if I draw the current here, now because these pulses are much narrower, then the changes in the current, it's going to be very smooth. So it goes up, it goes down a little bit, goes up, goes down a little bit, goes up, goes down a little bit, goes up more, goes down a little bit, and then goes up, goes down, goes up, goes down, yeah, and then eventually comes down more, goes up, comes down, goes up, comes down, and this would continue. And this looks much, I didn't do a good job drawing this, but it looks much smoother than what we had with only one pulse, because we have many pulses, right? Usually like the frequency of this carrier, like if this is 60 hertz, this is going to be in the order of kilohertz or megahertz, right? Small, like, sorry, the higher range of kilohertz, right? So then this would look much smaller, and then if you apply this to our motor, it would run much smoother, because this time it's gonna be much smaller. If this is like, if I call it delta t, if this time it's gonna be much smaller than the time constant of the motor, or the response time of the motor, right? So and because of that, the motor runs smoothly. We wouldn't have like that much harmonic. We still have harmonics, we still need to have filters, but compared to having only one pulse, which was the case here, then this would basically make our voltage and current waveforms, or sorry, our current waveform much smoother. Also for the voltage, if you calculate the Fourier transform and calculate the fundamental frequency, which is the 60 hertz frequency that you want to have, right? This is going to have much higher, much lower THD compared to this one, okay? So that's the whole concept of having sinusoidal PWM, that basically these pulse times are defined by the PWM, right? These pulse times, this is like how you turn these switches on and off, right? So these are defined by these PWM signals. There are like other methods of doing this. So one method is what you see here, sinusoidal PWM. The other method is space vector modulation, which is like nowadays more frequently used. And but also there are other methods called, like another method that's very famous, it's called like harmonic elimination. So it's basically creating these signals, but not using a comparator, not using PWM, by calculating the Fourier transform and trying to make the higher order components zero. So this is basically an offline method that you just like basically have to do your calculation and just like make these times, like these intervals, such that the higher order harmonics of this Fourier series of this signal becomes close to zero, or like becomes minimum, like based on the standard that you have. So here, like I showed you how to generate these PWM signals using a comparator. So that's one way of creating PWM signals. There are some ICs that create PWM signal. In ELEX 3130, you actually used an IC to create PWM. Also like 555 timer also create PWM. You can also, and like what's actually used in the industry is using microcontrollers. In your microcontroller course, you might have seen that